Okay, so in the previous section we learned a whole lot of stuff about exponential numbers, right? So first of all, what it is. By definition, it's this. B to the power n means that we multiply b times b times b n number of times, right? So for example, 3 to the 4th power is not 12. 3 to the 4th power is 3 times 3 times 3 times 3 4 times to give us 81, right? 3 times 3 is 9, times 3 is 27, times 3 is 81. Or you can group them. 3 times 3 is 9. The other 3's are also a 9, giving you 9 times 9 or 81. Okay, so that's what it was. And then we looked at the rules of exponential powers. What can we do with them? So we ran into this big list. So the first rule says that if we have two exponential numbers with that same base being multiplied, we add the exponents. Our second rule told us that if we have two exponential numbers with the same base being divided, we subtract the exponents in this order. The exponent in the numerator minus the exponent in the denominator in that order. Then we have, if we have a product being raised to a power, then we get to kind of distribute the exponent. If we have a division of exponentials, of values raised to a power, then again we do this sort of a distribution. Be careful that the c does not equal to 0. Remember that we're not dividing by 0. And then finally, if we have an exponential raised to another power, it means that we get to multiply the exponents, right? So these are the rules that we ran into in the previous section. And then we also ran into some situations. This, right? B to the 0th power is always equal to 1 for any value of b except 0. So 0 to 0 is just something we don't deal with in this class. But other than 0, anything else raised to the power of 0 is always a 1. And then the other thing we dealt with was, what if we have a negative in the exponent? If we have b to the negative 1, b to the negative 3, how do we get rid of that negative in the exponent? And the answer is we rewrite it as 1 over b to the positive exponent, right? So b to the negative n is equal to 1 over b to the positive n. Or if you start off life in the denominator, and it has a negative in the denominator, then to get rid of that negative with the exponential in the denominator, we move it up to the numerator and make it a positive exponent. Right? Okay, so we covered all those things in the previous section. Now we're going to add to it a little bit more by thinking about the following. So let's look at our powers, a table of powers. So let's say I have 2 to the power of 1, that's just 2. 2 to the power of 2, that's just going to be 4. 2 to the power of 3, well that's just going to be 8. Okay. 2 times 2 times 2, that's 3. Okay, how about, let's look at some other powers. How about 4 to the power of 1, that's 4. 4 to the power of 2, well that's just going to be 16. 4 to the power of 3, that's 64. How about something like a 9? 9 to the power of 1, well that's just 9. 9 to the power of 2, well that's just 81. Right? Okay, so we're comfortable with some nice integer value ones, some easy ones. So the thing we want to think about now is, what if we have a fractional power in the exponent? So for instance, what if we wanted to figure out what is, well I'll put it here, 9 to the 1/2 power. 9 to the power of 1/2. What should that be? How do we get an answer for that? I mean, clearly it belongs somewhere in the middle here. Let me just put it in there. Nine squared is 81. So we want to know, what is 9 to the power of 1/2? Right? It seems to make sense that it would land somewhere in there. Here's 9 to the 1, it's 9. I'm sorry, not between there. Let me think about it. Yeah, 9 to the 1 power is 9. 9 to the power of 2 is 81. We got 9 to the 0 is equal to 1. And so 9 to the 1/2 power, it seems like it would make sense that it would land somewhere between there. Somewhere between an answer of 1 and 9, right? Because it's being raised to the power of 1/2. So how should we figure out what that is? Okay, so that's what we're going to look at. Let's think about this. 9 to the 1/2. Well, it's equal to something, right? That's what we're trying to figure out. So let's just make it equal to some like W. W represents the answer. That's what we're trying to figure out. I don't know what it is, but it's equal to something, right? So now that I have it like this, what I'm going to do is I'm going to square both sides, right? So I'm going to take this side, 9 to the 1/2 power, and I'm going to take this side, and I'm going to take that to the power of 2, and take that to the power of 2. And so I end up with 9 equals to W squared. These are equivalent statements, right? So that weird, strange thing is equal to that. Yeah, question?
You're doing 2 because you want to get rid of the half?
Exactly right. Oh, okay, that's a great point. I should expand this. So from yesterday's ideas, we know that when we have one exponential raised to another power, means that we multiply the exponents. So that means that these two reduce and give us 9 to the power of 1 equals to that, or just 9 equals to W squared. We don't need the 1 there. So why did I do that? Well, because this looks really confusing, 9 to the 1/2 power, but it's equivalent to that, equivalent to that, equivalent. And now this is something we could probably kind of figure out, right? This is something squared equals to 9. Right? 9 is equal to something being squared. What is that something that goes in there?
3.
A 3. Right? So then that means that in there, W equals to 3. Is that the only answer? It could also be -3. Or W equals to -3. Okay, so, alright, we found our answer. When we have this, it equals to that. What about if we had a different one? How about if we had, I'll squeeze in here, 25 to the power of 1/2. Okay, again, I don't know what the answer is, so I'm just going to set it equal to something. How about y? I know, this should equal something, so how about y? And again, I'm going to square both sides to get rid of that half. Square it, y, square it. We know that this will be 25 to the power of 1/2 times 2 equal to y squared. The 2's cancel, giving me 25 equals to y squared. And again, this looks like something we can figure out. Something is being squared and the answer is 5. So this should either be a 5 or a -5, right? We can just kind of figure that out. The brute force method, it just makes sense. Something being squared is 25. That's either a 5 or a -5. Good? Okay, well, I think that if you think about it for a second, this thing is clearly behaving the same way as this. Right? What's the answer to that guy? Well, it's a number such that when you square it, it equals to 25. So I know that this answer here is 5. Right? Because it's a number such that when you square it, good? We'll deal with the fact that it's also -5 in 1 second. I'll come back to that idea in 1 second. But for now, it seems like this is somehow related to that. Right? And also notice that if there's nothing written there, by default, there's like a little negative, there's a little positive 2 there, right? By default, there's an invisible 2 there. And the same thing over here. It seems like this thing is somehow related to that. So 9 to the 1/2 power is related to the idea of the square root of 9. It's some number is being, we're looking for a number such that when you square it, it equals to 9. Right? Over here. This guy is also connected to the square root. So 9 to the 1/2 power is equal to the square root of 9. And it's behaving in the same way. Good? Okay. So how about if we had a power of 3? Let's say we had... If we had 8 to the 1/3 power, and we're trying to figure out what does that mean. Again, we can just set it equal to something, I don't know, some answer, A. And I can do the same thing, the same little trick, again, where we raise this to the power of 3. And so this is equal to A, to the 3rd power. Okay, over here, this is equal to 2 to the 3rd power. 2 to the 1/3 power times 3. The 3's cancel, giving you A to the 3rd power.
Where'd you get 2 from?
I didn't. It's supposed to be an 8 there, sorry. 8 equals to a to the third power. So now again, we're looking for some number so that when I multiply it by itself 3 times, the answer is 8. So it's got to be a 2. Okay? And so this is behaving the same way as this. Good? Sort of, kind of, maybe? Okay. So this is the rule. I'm just kind of giving you a sort of a sense for what the rule is going to be. But we can also try one more thing. 8 to the 1 power. Let's consider that. 8 to the 1 power is also equal to 8 to the 3 over 3. Right? 1 is 3 over 3. And now I know from my previous rules that I can separate this into 8 to the 1/3 power is equal to this. Let's separate it this way. Times 3 over 1. Which is equal to 8 to the 1/3 power raised to the power of 3.
Are you just showing us different ways to do it?
I'm trying to guide you in a different way as to figure out what the pattern is, and I'm not sure if I made it really clear in the other one, so I'm hoping maybe this will be more helpful. And I'll just jump with the formulas in 1 second, and hopefully it'll make sense at that point.
Okay.
Yeah,
So
question?
you did the 3 over 3 equals to 1, right? So we
Correct.
get that number.
So I started out with an 8, right? I started out with 8. 8 is equal to 8 to the first. And 8 to the first is equal to 8 to the 3 over 3 because this is a 1. 3 over 3 is 1. And I know I can break that up into this, 1/3 times 3 over 1. And finally I know I can separate it that way. So the reason I did all that is just to get this ugly thing and have some idea of what that means. This, whatever it is, right, I'm trying to figure out what is this 8 to the 1/3. Well, it's a number so that when you raise it to the power of 3, it equals the 8, right? Because all of these things are equal to each other. So if I just bring together this and marry it where we started, I know that 8 must be equal to something to the power of 3 when we have this like this. So if someone's asking what is that, one way to describe it is this, whatever it is, it's some value so that when you raise it to the power of 3, it equals to 8. And again, I'm just trying to get people to see that this is behaving the same way as this. Isn't that what this is? This is some number. The answer to this is some number so that when you raise it to the power of 3, it equals to 8. Good? So we want to make this connection right here. That 8 to the 1/3 power is the same thing as the cube root of 8. That's what we're driving at. Sort of, maybe? Is this?
Why do you have to be on the outside of the first one? So you're trying to cancel it?
So I wrote them this way and I separated them because I wanted to isolate this weird thing, right? My goal is to try and get you to see what this fractional exponent is.
No, I'm talking about the one more down. That one. Why do you have to be on the outside?
Because there's a 3 there.
You can't see that.
I just brought it down and I just rewrote this part this way. I was just pointing out that at this stage it's something that we don't know what this is. Whatever this is, it's something so that when I cube it, it equals to 8. Yeah, what is that something? It's got to be a 2, I know. But it's behaving in the same way. Because this is the same idea that this is some number. The answer to this is some number so that when you cube it, it equals to 8. Good. Like when you're trying to figure out, what is the cube root of 27? I'm looking for a number such that when I multiply it by itself 3 times, the answer is 27, right? That's what I'm looking for. The answer is 3 because 3 to the power of 3 is 27. That's why the answer is 3, right? And when we have like the cube of 64, the answer is 4 because 4 times 4 times 4 is 64. Good. So if we think of it in the same format over here, what this is over here, if I have if I have 64 to the power of 1/3 raised to the power of 3, and we're trying to figure out what is this weird thing in here, well, this is something that's equal to 64, right? I'm looking for a number such that when I cube it, the answer is 64. Well, hopefully we know that the answer is 4, which is behaving in the same way as this. So the answer is 4 because when we multiply 4 times 4 times 4, the answer is 64. And that's the same reason why this is an answer of 4. Good? Sort of, kind of. Okay, so all of these lead to the definition of what happens when we have a fraction in the exponent. So when we have b to the power of 1 over n, this is going to be the same thing as the nth root of b. We interpret these two things to be exactly the same. Notice that we have a positive 1 up here and an n right there. This is the nth root of b. Whereas here we call this the index of the radical or the nth root of b as well. Same thing. So for example, if we have 8, well let's just find a new one. How about 125 to the power of 1/3? That's the same thing as the cube root of 125. Right? And so the answer will be some number so that when you multiply it times itself 3 times, it'll give you the 125. We know the answer is 5. Good? Okay, so what if we have an even one, 64 to the power of 1/2? Well, this is the square root of 64. Right? Again, if there's nothing there, by default we put a little 2, if there's nothing there. So this is an 8. So 64 to the 1/2 power is going to be equal to 8. Okay? Now the rules are a little bit different based on whether this is a odd or an even index. When we have an even index, then we are not allowed to have a negative number in here. Or if we have a negative number in there, we're going to go into the imaginary section of the number system, and we don't want to go there now. So if you want to stay on the real number side, we got to make sure that this part is positive. So that's one of the rules that we're going to see. It breaks down into 2 parts, if n is odd or if n is even. If n is odd, then, that's just the answer right there. So if n is odd, then b to the 1 over n, where n is odd, is a number whose nth power is b, and it should be called, we call b to the 1 over n, the nth root of b. So that's kind of like this. This one's odd. This is b to the 1 over n, where b here is the 125. So it's equivalent to that, and the answer is going to be 5, and we call 5 the 3rd root of 125. That's what that first rule is saying. Okay? Now, if we have an even one, then we got to make sure, some conditions for us right now is that this is positive. We want to make sure that the b value has to be positive because it's being raised to an even root. And if it's not positive, then we're going to get an imaginary number. So we're not dealing with that yet. And also one more situation that sometimes we have to think about the positive and the negative possible results. If we have an odd index, then we are allowed to have a negative in here, and then the answer will be negative, right? So for instance, if we have negative 8 in parentheses raised to the 1/3 power, that's equal to negative 2. Negative 2 times negative 2 times negative 2 equals to negative 8. So that one's okay. But if we have 8 to the 1/3 power, well then that's just equal to 2. 2 times 2 times 2 is 8. Right? And again, if you're having trouble visualizing why it equals that, you could just rewrite this as the cube root of negative 8 or the cube root of positive 8. Good? Sort of? Kind of? With me? Sort of? Okay. Now, on the other hand, if we have an even index, then we got to make sure the b is positive, and also there might be positive or negative results. I'll show you the distinction in 1 second. The positive one, though, is called the principal nth root. So, if you are solving an equation and you needed to do something, like if you were trying to solve this, some number squared equals to 25, and in the process of solving it, you chose to raise both sides to the 1/2 power. Right? You did that. You decided, let me raise both sides to the 1/2 power. Then we end up with 25 to the 1/2 power equals to x to the 2 times 1/2, the halves cancel, so we end up with this. Okay, and so this is equal to the square root of 25 equals to x, which we know is 5, but because you decided to do that, you raised both sides to the 1/2 power, this is where we have to consider both the positive 5 and the negative 5. Okay? Because we were originally trying to solve this. If we go back to here, there's two possible answers. I can put in a 5, or I can put in a negative 5. On the other hand, if they just said simplify the square, simplify 25 to the power of 1/2, right? There was no original equation. There is, you didn't, raise both sides to a power. You didn't do any of that. They're just asking you to simplify this number here. Well, this number is the square root of 25, and this is just going to be a 5. And you don't have to consider the possibility that it might be negative. By default, they always refer to the principal root, the positive root, unless they specify otherwise, unless they specifically told you to think about the negative one. Sort of, kind of, yeah.
The 2 is still there, right?
Yes, by default, if there's nothing written there, by default we like to think of it as a 2, but many books and situations, they just don't bother with putting that little 2 there. It's an invisible 2. Good? Questions? Yeah.
The reason why that one has 2 is because of x squared, right?
It's because if we go back to the original question, there are two possible things that can happen here. I can put in a 5, or I can put in a negative 5. So there's two possibilities to the solution of this. So we started out with an equation, and I chose to raise both sides to the power of 1/2, which is what leads to this. And so yeah, there's two possibilities. Okay? Alright, so these are some examples. How about this example, number 25 to the 1/2 power? Well, we've been doing that all day long, right? What is it? 5. And we don't think about negative 5, it's just 5, because they just gave us this to simplify. What about 64 to the 1/3 power? 4. 4 times 4 is 16, times 4 is 64. What about negative 64 to the 1/3 power? Negative 64 to the 1/3 power. Well, that's just the cube root of negative 64, which is equal to negative 4. Good? Right? Notice that negative 4 times negative 4 times negative 4 does exactly equal to negative 64. So we don't have to worry about the other possible answer. There's only one. It's a negative 64. There's only one answer. It's got to be negative 4. Positive 4 is not a potential answer. Good? Same thing with positive 64 to the 1/3 power. 4 is the only possible answer. Negative 4 is not a possible answer. Good? What about 16 to the 1/4 power? 2. What about negative 16 to the 1/4 power?
Negative 2.
What's the difference between the two? 16 to the 1/4 power is the same thing as the 4th root of 16, which is equal to 2. And negative 16 to the 1/4 power is equal to negative 1 times 16 to the 1/4 power. In a case like this, because we didn't put parentheses, the 1/4 does not apply to the negative 1. So this is negative 1 times the 4th root of 16, which is equal to negative 2. Okay. What about the next one? What about negative 16 to the power of 1/4? Now the 1/4 applies to the whole thing. This is the 4th root of negative 16, and this equals even root, negative number, imaginary solution, right? No real solution. No real number solution. There is an answer, but the answer is part of the complex number system, which involves imaginaries, and we're just not dealing with those yet. So for us, it's just no real solution, right? By no real number solution. Good. Even root, negative in the inside the radical, no real number solution. Questions, 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 questions? Okay, so now that we have fractional powers of the form 1 over an integer, then we can revisit all our rules. What if we had 8 to the 3, well, let's make it 2/3 power, not a 1, how do we deal with that? Well, for this one, what we would do is simply rewrite this as 8 to the 1/3 times 2. And then this can be rewritten, right, times 2 over 1. So this could be rewritten as this, as we've done before. And now what we have is the cube root of 8. Cube root of 8 squared. And the cube root of 8 is 2 squared. So it's going to be 2 squared or just 4. There's our answer. Okay, so the way we deal with a fraction that doesn't have a 1 in the numerator is going to be to separate them. Now you can separate it this way, or you could have also separated them this way. You could have written it as 2 over 1 times 1/3. In other words, just flip these around. Doesn't matter. And so this would have been 8 squared raised to the 1/3 power, which would have been equal to 64 raised to the 1/3 power, which is the cube root of 64, which we know is 4. Same answer. Right, so different paths to the same answer. Good? Good, good, good. Okay, so separate them and deal with them that way. And in general, the formula is this. If we have a b to the m over n, then we can rewrite them as b to the 1 over n raised to the power of m. So deal with that fractional exponent. Or we can also deal with it in the other direction. Maybe we put the 1 over n on the outside and deal with it afterwards. Good? Good. If we have a negative in the exponent, well then we do the same thing. We just flip it underneath 1 and then we work in the same way. Good? Sort of, maybe, kind of. Good. So, for example, let's simplify some of these. F of x equals to 64 to the power of x. So f of 2/3, right? Because it's the f function, I go over to the 64 to the x power. So this should be 64 to the power of 2/3. That's what we got to simplify. So we can separate this into 64 to the power of 1/3 times 2, which is equal to 64 to the power of 1/3, all of that raised to the power of 2, since we know that an exponential number raised to the power is equal to the product. And now this guy, we can rewrite it as the cube root of 64 squared, which is then equal to 4 to the power of 2, which is then equal to 16. Good. Okay, that's one way to do it. Lots of other ways to do it. How about at this point over here, right? I'll put a big or. At this point, we could have rewritten this in a different order. 64 squared times 1/3, so like that. So this will be 64 squared, all of that raised to the power of 1/3. And so what's 64 squared? 4,096 to the power of 1/3, which is equal to the cube root of 4,096. And I know that's going to be 16. I'm going to get the same answer at the end of the day. Right? So they're both the same. It's just, the order. Do you want to square first and then take the cube root? Or do you want to take the cube root first and then square? Right? I think most people might agree that the top one was a little bit better. There's more options though. Or you could factor out the 64 first. Find its prime factorization and you'll see that stuff simplifies a little bit better. So if we know that 64 breaks down into a 4 times, let's go with 8 times 8, 2 times 4, 2 times 4. Each of these 4s break down into 2 and a 2 and a 2 and a 2. 1, 2, 3, 4, 5, 6. Okay, so that means that 64 is equal to 2 to the 6th power. So what I could do is I could take the 64 raised to the 2/3 power and rewrite it as 2 to the power of 6 raised to the 2/3 power. And now that simplifies into 2 to the 6th times 2 over 3. This cancels with that, giving me 2 to the 4th power, which is again equal to 16. Same answer once again. I'll do one last one. If we notice that we have, we're dividing by 3 up there, it might be nice to have a power of 3 there. You might remember, you might recognize that 64 has a nice power of 3. So you could write 64 to the 2/3 power as 4 to the power of 3. That's what 64 is. Raised to the 2/3 power. And now this would be 4 to the 3rd times 2 over 3. The 3's cancel, giving you 4 squared. Again, getting to 16. At least 4 different paths to the right answer. Which one's the best one? Whichever one you like best is best. Whatever one makes most amount of sense. In some situations, you'll find that maybe, doing this kind of situation might be better, or going down here. Me personally, I really like factoring things, so first thing I do with things is factor them out. So I probably would have gone with this route or this route if I noticed it. If you notice that the 3 will cancel out nicely, great. But in more complicated situations, when they get really nasty, it's hard to see some of those shortcuts. So I just go straight to finding the prime factorization of everything, and I find that works out well for me. But as you practice some of these, you'll get your own ideas. Good. Any questions on any of these? They're all the same, right? Good, good, good. Okay, what about number 2? G of 3/4. So now we got to go over the G function. And we got 3 times 16 to the power of x. So we got to evaluate it at 3/4. G of 3/4 is equal to 3 times 16 to the 3/4 power. Okay. So again, lots of different paths toward the answer. We could do this thing, 3 times 16. No, I'm going to go down. Working that way is going to be ugly. Let's go this way. I could rewrite this as 3 times 16 to the power of 1/4 raised to the 3rd power. Right? Breaking this up into 1/4 times 3 and raising that to the 3rd power. Then this would become the 4th root of 16 being raised to the power of 3, which is 3 times, and then this is equal to 2. The 4th root of 16 is a 2, raised to the power of 3. Well, that's just going to be 3 times 8, which equals to 24. Right? So there's my answer, 24. But lots of different paths to the answer. We could, again, do it the other way around if you want to. We could say that G of 3/4 equals to 3 times 16 to the 3/4 power. We could rewrite this as 16 to the 3rd power raised to the 1/4 power. Separating them that way, because I know that when I multiply these, it equals to 3/4. But then I'd have to figure out what 16 times 16 times 16 is. People with calculators, it'll help. 16 to the 3rd power is
4,096.
4,096. Okay, then this would be 3 times the 4th root of 4096. I'll save you some suspense. It's got to be an 8, because I know it's got to be the answer to this one. So I know I'm going to ultimately get the same result. Good, good, good. Two paths to the answer. Here you'd have to kind of multiply some stuff. I'm sure you could do it. If there was a task like don't use calculators, that might be a little bit more difficult to first of all cube that, and then second of all figure out that that's the 4th root is that. So this might be kind of hard without a calculator. This one's a little more doable, right? The numbers were a little easier. I mean, all I have to know is that the 4th root of 16 was a 2, and that the cube of 2 is an 8. So the numbers stayed a little smaller in this direction. So it seems like this might have been a little better in this case. But in another situation it might turn out better to cube it first and then take the 4th root. Depends on what the value is. If this is a very small number that maybe does well when you cube it, get a nice whole value or something, you might want to do that. Or yet another one, last one here. How about if I again find the prime factorization of 16? 16 is 2 times 2 times 2, 4 times, right? So 2 to the 4th power is 16. So I can rewrite this one, g of 3/4 equals to 3 times 16 to the 3/4 power. I can rewrite it as 3 times 2 to the 4th power raised to the 3/4 power, right? Because 2 times 2 times 2 times 2 is 16. And now this is equal to 3 times 2 times 4 to the power of 3/4. The 4ths cancel, giving us 3 times 2 to the 3rd power, which is 3 times 8, which is equal to 24 once again. Any questions? No? No? No, no, no? Okay, how about the last one? H of negative 1/2. So now we gotta go over the H function and figure out what that is. So H of negative 1/2 is equal to negative 5 times 9 to the negative 1/2. Okay, and how do we deal with a negative in the exponent? Put it underneath 1. So this is negative 5 times 1 over 9 to the positive 1/2. And now 9 to the positive 1/2 is equivalent to 1 over the square root of 9. And so this is equal to negative 5 over 3. Do we have to think about the possibility of it being negative 3? No, right? This was not an equation. I wasn't trying to solve for x. I didn't square or cube root both sides. I didn't do anything like that. So this is by default referring to the positive, the principal root of 9. So this is the only answer. Good? Good. What's another possible way of doing this? Well, if you notice right away that 9 is equal to 3 squared, h of negative 1/2 is equal to negative 5 times 9 to the negative 1/2 power. So this is negative 5 times 3 squared, that's what 9 is, negative 1/2, equals to negative 5 times 3 to the 2 times negative 1/2. The 2's reduce, giving me negative 5 times 3 to the negative 1, and to get rid of that negative in the exponent, it's negative 5 over 3. So, same answer. Any questions? Okay, so all the same rules apply. When we're multiplying exponential numbers with the same base, we add the exponents. When we're dividing exponential numbers with the same base, we subtract the exponents. When we're multiplying two values and raising it to a power, we do this distribution of exponents. When we're dividing two values, raising it to a power, we can distribute the exponent. And finally, when we have one exponential and raise it to another exponent, another power, we multiply those powers. And this is true if the exponents are also fractions. So in the previous section, we only dealt with integer values, but now we get fractional values up there as well, and all the same rules apply. So how about simplifying that? B to the 2/3 times B to the 1/2. Okay, so what rule, what property helps us here? When we're multiplying two exponential numbers with the same base, we get to add the exponent. So this is b to the 2/3 power plus 1/2 power. We add the exponents. And now we gotta simplify, we gotta get a common denominator. This is equal to b to the 2/3 plus 1/2. And what I'm gonna do is I'm gonna multiply this by a 2/2 and this by a 3/3. And then that'll lead to b to the 4/6 plus 3/6, which leads to b to the power of 7/6. Good? Questions? No? Okay, what about this one? How about 32b to the second power divided by b to the 32nd power? All of that being raised to the power of 2/5.
Do we leave that as is the b to 7/6?
Yeah. Okay, so let's convert the 32 into its exponential or its prime factorization. 2 to the power of
Is it 5?
5, right? 2 to the power of 5 is 32. 2 to the power of 5 is 32. We can do its prime factorization. 2 times 16, 2 times 8, 2 times 4, 2 times 2, 1, 2, 3, 4, 5. Okay, that's all I'm going to do here. Here to here. Raise the 2/5 power. Okay, now I can simplify these two. Oops, this was a 12, not a 32. 12. Okay, so now I can simplify these two. I know that when I have exponential numbers being divided, I can subtract their exponents. This is going to be 2 to the 5th power times b to the power of 2 minus 12. All of that being raised to the 2/5 power. So this is going to be equal to 2 to the 5th power times b to the negative 10 power. All of that being raised to the positive 2/5 power. Okay, so now put this over here. So now this is going to be equal to 2 to the 5th power times, and then how do we deal with the negative in the exponent? We flip it, write it underneath 1, make it a positive exponent. All of that still being raised to the 2/5 power. So this is 2 to the 5th power over b to the 10th power. All of that raised to the 2/5 power. Okay, then we get to distribute. This is equal to 2 to the 5th power raised to the 2/5 power. All over b to the 10th power raised to the 2/5 power. Now we multiply the exponents. This is equal to 2 to the 5 times 2/5. All over b to the 10 times 2/5. And then put a little 1 there, put a little 1 there. The 5's cancel there to give me 2 to the 2nd power. And then 5 and the 10 reduce to give me b to the 4th power. And so my final answer is 4 over b to the power of 4. That's a long 1, 2, 3, 4, 5, 6, 7, 8, 9. I took like 10 steps to do it. You do not have to do it in exactly the same way I did it. You don't have to take all these steps. I'm doing it so that you can follow my work and, you know, kind of keep track of things. But if it takes you only 3 steps to do it instead of 10, that's perfectly okay. So as long as you're comfortable with the steps you're taking and you know why you're doing it, if somebody questions you, why did you go from there to there, then as long as you're clear about it, that's fine. But you're not required to take 10 steps. But if it helps, then I would encourage it. If you're still a little confused, then it's worth going the extra mile and making sure you're really clear on why, you know, we're manipulating the variables the way we do. So if it helps, do it. If not, if you're comfortable with less steps, then that's perfectly okay. Okay. Any questions on any of these steps? No? 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 Okay. So it's just getting uglier and uglier, right? How about that guy? 81 b to the 6th, c to the 20th, raised to the 1/2 power, all divided by 27 b to the 12th, c to the 9th, all raised to the 2/3 power. Okay. 81 b to the 6th power, c to the 20th power, the whole thing is being raised to the 1/2 power, divided by 27 b to the 12th power, c to the 9th power, all of that being raised to the 2/3 power. Pretty ugly. Can I start reducing 81 and 9? I know they have like a 27, they have a 9 in common. Can we cancel that? 9 goes into 81, 9 goes into 27. Why not? Because they're being raised to different exponents, correct. If this was one big happy fraction inside one giant parenthesis raised to an exponent, that's fine. Or even if these two were the exact same exponent, that would be fine as well. But because they're different, I can't do that. I got to deal with that first. So what I would do first is, my favorite is to go to its prime factorization. This is, well, you can think of it as 9 squared. And I know that that helps because there's a 2 there. So I know that 9 squared is a perfectly good way to represent this. Or if you go all the way back down, it's really 3 to the power of 4. Right? When you find its prime factorization. And this guy's going to be a 3 to the power of 3. So let's write it that way. 3 to the power of 4, b to the power of 6, c to the power of 20. All of that being raised to the power of 1/2. All of that, all over 3 to the power of 3, b to the power of 12, c to the power of 9, all of that to the 2/3 power. So all I did is I converted the 81 into 3 to the 4th and the 27 into 3 to the 3rd. And now I got no other choice, there's no other way to simplify this except to distribute the exponents. So this would be 3 to the 4th raised to the 1/2, and b to the 6th raised to the 1/2, and c to the 20th raised to the 1/2, all over 3 to the 3rd raised to the raised to the 2/3, b to the 12th raised to the 2/3, and c to the 9th raised to the 2/3. Right, so we distribute to each one. Squeeze that over here. Okay, so here we have 3 to the 4th raised to the 1/2. I know they're going to reduce and give me 3 to the power of 2. And then b to the power of 3. And then c to the power of 10. Divided by, and now here, the 3's cancel, giving me 3 to the power of 2. And here, 3 goes into 12 4 times 2, it's going to be b to the power of 8, and c to the power of 6. Okay. Well, now I can reduce things, and this are identical. I know they're just going to cancel. And this is going to be b to the power of 3 minus 8 times c to the power of 10 minus 6, which equals to b to the power of negative 5, c to the power of positive 4. And the way we deal with that negative in the exponent, we put it underneath 1. This will be 1 over b to the 5th times c to the 4th, which ultimately just gives you c to the 4th over b to the 5th. That's final answer. Again, you don't have to do every little step the way I did it. 1, 2, 3, 4, 5, 6, 7. I took 8 steps to go to finish this guy, but you don't have to take this many steps. If you go from here, it's very reasonable to go from there to like there, and from there to like maybe this step, or this step. It's sort of up to you and how comfortable you feel with the material. Yeah.
And you got the 3 from factoring the 81, 27?
Correct. 81, if I find its prime factorization, it's 9 times 9, and then each of those 9s is 2 3's to give me a total of 4 3's. And the 27 is 3 times 9, and then one of those 9s breaks down into 2 3s. Good, 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 good. Okay, let's try this guy. How about b to the 3n plus 4, b to the n minus 5, divided by b to the 2n minus 3, all of that raised to negative 1/2 power. Okay, simplify this. Okay, so we know that inside the parentheses, can we start reducing things right now? No, because that has a certain power up there, so really can't do it yet. But inside the parentheses, we can simplify this a little bit, because I know that these are two exponential numbers with the same base of the b. So I know that this is going to be equal to b to the power of, and what do we do with the exponents? We add them. So this would be 3n plus 4 plus n minus 5. And then all of that is being raised to the power of negative 1/2. And then all of that is all over b to the 2n minus 3. So now we can combine some like terms up here. Right, so I'm just adding those. All of that is up in the exponent. So it'll be 3n plus n. That's going to be equal to b to the 4n. And then I have a plus 4 minus 1. And all of that is being raised to the negative 1/2 power. And all of that is being divided by b to the 2n minus 3. Okay, so now let's put this guy over here. So now let's go ahead and distribute that negative. What happens when I have an exponential number raised to another power? What do we do with them? Like if I have 3 to the power of 2 raised to the power of 4, what do we do with the 2 and the 4? We multiply them. This is 3 to the 8th power. So that's what we have here. We have this to the power of this being raised to that. So we multiply those two. So we'll get b to the power of 4n minus 1 times negative 1/2 divided by b to the 2n minus 3. So now we multiply, we got to distribute this minus, so we'll end up with b to the power of negative 2n plus 1/2. Good. And then the denominator stays the same. B to the 2n minus 3. And now we know that when we divide two exponential numbers with the same base, what do we do with the exponents? Subtract them in this order. We got to have b to the power of negative 2n plus 1/2 minus 2n minus 3. What am I doing wrong there? Something's wrong. Parentheses, I got to make sure I throw them in there, right? Because it's subtraction of everything down there. And the way I've written it, it's just subtraction of this one. So I got to make sure I insert these parentheses because it's minus that whole thing. Which means I'm going to have to distribute that minus. That's what the difference is. So this is going to end up being b to the power of negative 2n plus 1/2 minus 2n plus 3. Okay, and so now we can combine some like terms. These two combine to give me b to the negative 4n. I'll just put over here. B to the negative 4n. And then these two are going to combine to give me, well, as a mixed number, I can think of it as a 3.5 as a mixed number. Or I can think of it as a decimal, 3.5. Or I can think of it as a fraction. So b to the negative 4n plus 7 over 2 is another good way to put it. Or 3 to the b to the negative 4n plus 3.5 is another good way to put it. Good. Weird.
or we could have written it as b to the negative 4n plus decimal fraction, how about 7/2? Right, so either this one, or this one, or this one, they all mean the same thing. Any questions? No? 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 Okay, I think that's a good place to stop.